Firmware is quite a unique and challenging domain.
If your firmware's designed poorly, you might be able to compensate for it by running more expensive hardware. So there's a trade-off. Good firmware balances the constraints and uses the resources it has efficiently.
But if you need to be doing things asynchronously or in parallel, that's when the real challenges of firmware come in. Really.
Well, it usually gets hard once the firmware has to interface with an external device, which is what IoT is. In software, something that's good is usually something that doesn't piss off the user, I suppose.
Hi and welcome to the Engineering Triangle, our podcast about how to make the best smart machines and IoT as fast as possible. I'm Ayrton. Today we'll be focusing on how we do firmware design here at Element. I'm here with Sam Moore, our Senior Firmware Engineer. Sam has 8 years experience in firmware design, developing the interface between electronics and software. Thanks for coming on.
Thanks for having me.
You're welcome. So the first thing I basically want to talk about with firmware is what is firmware? Because not many people understand what firmware is. A smart device that you use asks you to do a firmware update. That's what most people's interactions with firmware is. But basically, firmware is the software that runs directly on the hardware, the electronic chips. Is that right?
It's just fancy software, I suppose. But usually in firmware, you're focused more on interacting with the real world, I suppose, rather than abstract concepts like controlling outputs and reading sensors and stuff like that.
Yeah. So some examples of firmware that we've done here at Element is little tiny Bluetooth microcontrollers that would be interfacing with sensors. So the ShockWiz device interfaces with a pressure sensor, interfaces with 3-axis accelerometers, interfaces with Bluetooth, so the electronics that actually makes the Bluetooth wireless communications, and how that microcontroller does all of those things in a timely manner to enable a person to interact with the device via Bluetooth, or the device to do its own job at sensing what the person's doing on the bicycle, things like that. Firmware is quite a unique and challenging domain. Sam's got a history with physics and mechatronics and came to the business back in 2015, 2016?
2016.
Yeah, 2016. Started off as a testing engineer, interfacing with the devices that we were creating for the ShockWiz at the time, and has then gone on to basically become our senior firmware engineer, working on all the electronic devices that we've created over the years. So, and Sam and I also made some decisions early on about 2018, to try and make firmware a bit easier to do here at Element as well. To start off with, what makes for good firmware design?
In software, something that's good is usually something that doesn't piss off the user, I suppose. But with firmware, it's the part of the software that the user doesn't see as much, so it's a bit harder to tell. I have 2 robotic vacuum cleaners, and I won't say what brands they are, but one of them is good and the other one is But without actually knowing how the code's designed, I can't really comment on what's good about their design or not. I suppose a good firmware design usually involves a lot of testing. It's similar to other software. You use modular design, you use testing, you use a lot of the same techniques, but there's the added complexity of often having to understand the electronics behind systems. Like if you're driving a motor, you usually have to understand how that circuit's going to work, at least on a basic level.
Every IoT widget that you buy these days has firmware in it. Some examples of good firmware, exactly what you said before, something that doesn't piss off the user. And the user basically has a somewhat seamless user experience to make it work, and the thing doesn't complain. And
it doesn't beep at you like certain robotic vacuum cleaners do.
I think in my house at home, I've got sort of smart home set up with SensorBo air conditioning devices. They just seem to be very, very seamless. It's quite a simple widget really that basically proxies your commands from your phone, but connects through the internet, and then does a infrared remote control to your air conditioners. That's just a really nice, seamless user experience. And sometimes they want firmware updates or whatever, and they sort of tell you about it, and it takes a few minutes to do the firmware update, and that seems nice. So, but there's Chromecast and things like that. They're kind of going next level where they're actually running an operating system. So firmware is usually not like an Android operating system, or it doesn't have a full operating system on it. It's basically the core that interfaces directly with the electronics. And more simplistic devices in a way, which a lot of the time may actually have to be doing quite complex things with sensors or actuators. worst case scenario, what are some of the worst examples of firmware design that you've seen?
Well, I mean, I haven't actually seen a lot of terrible firmware. Usually stuff mostly does what it's supposed to do. You can tell if something's poorly designed because it's usually not very responsive, and that's usually becomes reflected in the user interface, which is outside of firmware. But there are other implications, I suppose. If your firmware's designed poorly, you might be able to compensate for it by running more expensive hardware, and that will make the firmware work because you have more powerful processor or whatever.
Yep.
But it'll make the electronics cost more. So there's a trade-off when you make those decisions. And I guess good firmware balances the constraints and uses the resources it has efficiently.
That's a really good point, because I guess firmware is usually the software that goes directly on the chip that controls all the peripherals around the chip. But there's any number of different chips that you can buy. You can buy electronics microcontroller these days from $1 all the way through to hundreds of dollars. And when you're mass producing something in the hundreds or thousands or tens of thousands of quantity, you've got to make a choice on what those things are. Firmware primarily runs C code, and you have a certain amount of limited resources as well. So you've only got usually one CPU, although some of them are coming out with new multi-cores these days, which means you can kind of do one instruction at a time. And you've got limited RAM resources, so you can only hold a certain amount of information within the chip itself, and you might only have access to rudimentary sort of storage and things like that. So the firmware engineer's role really is to balance what the requirements of the device is, and do those things in a timely manner that's going to be the outcome of the customer.
To focus on the RAM example, you might want to compensate for not having much RAM by adding external RAM to your design, but then the firmware now has to interface with that external RAM.
Yeah.
So it's a trade-off you have to make whether or not it's worth the extra complexity of having the RAM controller and all of that stuff.
In firmware design, you often have to create sort of an operating system of its own. So you can use it as a device that basically just runs a script, almost like an Arduino, where it initializes some peripherals, then runs specific functions on those peripherals and just loops back around. That's kind of the simplest firmwares that we can run.
Yes.
But if you need to be doing things asynchronously or in parallel, that's when the real challenges of firmware come in. Really.
Well, it usually gets hard once the firmware has to interface with an external device, which is what IoT is. Everything has to talk to Bluetooth or, be on Wi-Fi or something like that.
Yeah.
And you normally have to have other tasks that are running at the same time. Like for HydraTune, it's got to be moving the motor at the same time as it's updating the readings to the app. Yeah,
firmware is an unusual field, and I guess it's not really truly appreciated how complex it is. Yeah, it's nice to be talking about it today. What is the key to developing firmware quickly?
This is a hard question. Normally with software, like conventional software, there's a lot of libraries and frameworks that people will use, which will save them from having to do some of the low-level coding. In firmware, there are tools like that you can use, but you have to be a lot more careful, but mainly because of the limited resources. And also, a lot of vendors have their own different tool sets and libraries, and it's not necessarily trivial to pull those things together if you want to use them together. Generally, what we try to focus on is identifying the features, and maybe sometimes it's better to simplify the feature set of what the firmware does rather than looking for like a silver bullet library that you can download off the internet that does everything for you. Because if the tools do too much stuff, you don't really know what the scope of the firmware is. So it's also better to focus on the functional requirements of the firmware. A lot has been said in software about patterns and best practices, and it's not like you shouldn't obey those rules in firmware, but sometimes, you have to take shortcuts that might be frowned upon because it's a different way of working. You're not building this huge monolithic feature set. You're focusing on making the thing do the one thing it's supposed to do. So an example, which is maybe a bit technical, but would be like a singleton pattern, which is generally seen as bad in software, even though I think it's used in software anyway, but they'll teach you not to do it. Whereas in the firmware, we end up doing that. Like the a simple firmware can maybe only respond to one request at a time, whereas a more general high-level software design, it has to respond to any number of requests up to the however many the CPU can handle. But that changes the way you design the code a little bit.
We're talking about a $3 microcontroller that might operate at 64 megahertz. You're sort of talking the same computational resources as like a late 90s PC kind of thing. And the RAM might be in the 64 kilobytes of RAM, something like that. It's tiny, like no file that you get off the internet. You know, when you download a web page on the internet, when you're looking at that browser, there is more information coming through just to show that web page than we have for the whole RAM required for running a device that might control your air conditioner or might control part of your mountain bike or something like that. So the resource limitations are the major factor, and firmware is its own art because we are trying to work within those limitations. We're directly interfacing with the electronics that are surrounding the devices, and you're trying to do smart things with a great user experience where people see that or don't feel that, and they have a seamless user experience as well. So yes, you can definitely buy faster microcontrollers that have more resources, but it's going to cost you more to make that widget. And it's also going to have more implication on the firmware design role, right? Like you're going to have to create a driver and then create a system that can integrate those more complex resources anyway.
In some ways, it actually helps to have the limited resources because you can restrict your scope a bit more. If you have all of the resources in the world, you might get too excited about what you can do with them.
Yeah, that's pretty interesting. How is firmware design different to other forms of software development?
I don't know what the electronics engineers think about it, but firm is in between hard and soft. So it's in between hardware and software. But at least the type of firmware we write here is more similar to software. The main difference is, you have to be aware of how the pins are mapped on your microcontroller and things like whether there's a pull-up resistor or a pull-down resistor.
Yeah.
Some of the things we do is like verifying the electronics design, like that stage sort of happens in firmware. Obviously, they test everything they can before that, but there's still things that might get missed.
So one thing with firmware development that I think is quite different to software is we have to basically write drivers, right? Write the drivers that are basically configuring the different input-output pins, then is talking with a peripheral. Either it's an analog input, it could be a digital input, it could be an array of multiple digital inputs. There could be a communication protocol or a bus. So you might have USART or SPI or I2C, those sorts of things. And there may already be drivers that are written, but a lot of the time we'll create drivers that are interfacing with those things. And then we'll go to the next part of the software, kind of the operating system, I guess, or the control system within the firmware itself.
There's usually layers involved in software, I suppose. So we have controllers, which is basically talking directly to the registers on the electronics.
Yep.
So in that one, you're pretty much constrained to what the electronics design has determined, right? So electronics isn't software. They can't just add JSON blobs into their CPUs or whatever. There's usually some electrical circuit involved. That's why this bit of this register is assigned to this value or something like that.
Yep.
So the starting point is usually modeling that in C. We define C data structures to represent all those registers. And then we try to make a common set of peripherals out of that. So the peripherals is the next layer up you were mentioning, like USART, SPI, that type of stuff. Those are common things that we expect most systems to use, and we write functions we can call out from there. In our design, we usually try build a network interface or a network link around that.
Yeah, because we're doing everything in IoT. And
it gets a bit vague, but for our model, we have the network link layer and network interface layer, which are really kind of the same layer in our design, but they're kind of separate. I guess a network interface is a generic abstraction for something that, sends data to a network, and the network link is the actual implementation of that. So we have like an RS485 link or a Wi-Fi link or a Bluetooth link. From the network layer, we create things called sockets, which is like our data streams. And then for us, we have our own message service, I suppose, which is that's where the API design comes in, where we're designing things that other software can control by sending specific messages.
Yeah. Sam and I made a decision back in 2018 after doing a couple of different projects for IoT with different customers, and we had different projects which were all structured in firmware in different ways. And it was quite hard to not only work on a new project, but to have the same people working on a different project or bringing them across. We kind of made a decision in 2018 to let's do firmware and the software all the way through the entire stack, from chip to the internet, chip to app, and chip to sort of the front end, have all of those layers talking in the same language. And that's been a long and very valuable process, because now we've created an ecosystem that allows us to conquer any of these specific domains and still use the same firmware applied to the different parts.
I suppose you could say there's more focus on functional requirements than visuals. Like, we still have all the same things like arguing about programming languages and all of that regular software has.
So one major difference between firmware and software is obviously memory, but in firmware, to have performant firmware, we are controlling the memory directly. So a lot of the software languages that a lot of web developers will use are already have a memory management system, or anything that you're running on an operating system.
It's very complicated, but yes, we use compiled programming languages in firmware. It is possible to use interpreted languages or VMs like Java and that, but they all require more resources, and usually you spend so much time getting those things to work that you don't have any time left over to actually make the firmware do something. I guess that would be an example of a mistake in firmware design, where you spend all this time trying to get Python running on your hardware and don't have any time left over to actually implement something, or you do implement something, but because it's in Python, it's too slow. And
there's obviously systems out there that are already doing that have got Python or MicroPython running on. And another difference would be, say, Rust. People are using Rust now, which is a memory safe
Rust is
language.
very popular. We haven't had the chance to use it here yet, though, so don't know too much about it. I looked at it. It has weird syntaxes. I've been told it's good.
But memory management, or having to manage your own memory, I guess, is something that a lot of software engineers wouldn't be doing generally.
Well, we try not to use too much dynamic memory allocation, but it's sort of unavoidable the way our firmware has evolved. So we do have dynamic memory management, but it's up to the programmer to free their memory most of the time. And make sure you're being safe with it and not overriding someone else. Yes, we do design things in a way that makes it easier with event systems and stuff like that. But we don't have garbage collection. You can't just add stuff to structures dynamically, like the structure's pre-compiled. So
it's getting deep. We helped design and manufacture Cuda Dairy's HydraTune system for technicians to remotely perform maintenance on dangerous hydraulics out in the field. Part of that project was firmware design. How do you and your team approach this, and what did you learn?
The team was me and Jonathan at the time. Jonathan got to concentrate on the lower level code, which is the driver for the stepper motor. We have to control the current and phase of the stepper motor. So Jonathan worked on that part, and I basically did the API and communication between the two processors. There's two processors involved in that. One for Bluetooth and one for the motor control.
So the motor control is quite a powerful chip, runs at a much higher clock speed than the Bluetooth processor. If we use the Bluetooth processor, we can have the Cranio firmware on that device, but it may not have enough resources to be able to do the Bluetooth communications and do the control system communications in one.
And we don't want the stepper motor being screwed up because of some Bluetooth thing. I guess another thing about the Bluetooth is we get a soft device that comes from the vendor, and our firmware runs on top of that soft device. But the soft device takes total control over all timers and interrupts. So it's pretty good. Like, Nordic's done a great job with it. But if you really want something to happen exactly at this specific time, it's not really guaranteed, especially if there's a lot of Bluetooth transmissions happening in the background.
So the HydraTune device is a safety critical device that basically takes the Bluetooth communications from an app, Bluetooth app, and has to basically perform real time control of a stepper motor. So you've got a lot of things happening in parallel. You've got to basically be communicating consistently with the Bluetooth app. You've then got to be looking for commands from the user and then executing those commands on the actual stepper motor itself, feeding back its real-time position. So you might say, I want to move 10 degrees, but that wouldn't happen instantaneously. There will be some actions happening and some real-time feedback.
I guess that's another difference between software and firmware is some of the interactions in firmware take longer to happen than they do in software.
Limited resources.
I mean, if you used a web browser, it seems like everything's slow, but most of that's just network traffic. Whereas in firmware, sometimes, it's physically not possible for a stepper motor to move 90 degrees instantaneously.
Yeah. So a major part of the design of the HydraTune device was actually having separate processors. One processor dedicated to basically Bluetooth communications and asynchronous communication with the real-time processor. The other processor was basically looking at all the sensors because we have a pressure sensor, we have some, current sensing and temperature control, things like that, and then actually doing the output to the stepper motor, and then taking that feedback and communicating. So we actually used our Cranio ecosystem, which we have assets in electronics, firmware, web, and app. Assets. We use that as the basis of design for Kudaderi's HydraTune system, and then we basically created those specific drivers and specific control system over the top and applied it to the customer, which is what the customer pays for, and that's the outcome that they get. Given that it's safety critical, the role of the firmware being asynchronous and having one processor doing Bluetooth and comms and having the other processor being able to make sure it's available to be able to do real-time control and take those asynchronous communications is a challenge. And a challenge that I think you've addressed pretty well, Sam. But that's been a major part of your work for the last sort of 3-4 years, right?
Yes. And I'd say with HydraTune, we kind of had, proof of concept working, but the major challenge with getting that ready would be the performance. So we ended up having to optimize a lot of stuff to get that responding to the app, sending all those pressure samples at the same time that it was moving the motor. Yeah,
we had Ravinder on the podcast last week. He was sort of saying that you and him worked very closely together to basically.
That's correct. Yeah. And that was very helpful because unfortunately there may be a certain way to do something that makes it very easy for the app, but it's not necessarily making it easy for the firmware or in this case, it might not even be safe. I think the first assumption is we'll get the app will move the dial to a position and it'll just send one command to the firmware and the firmware will go move 45 degrees or whatever. I don't know what that translates to in the movement of the actuator, but it would, you want to move it quite a large distance, but once you've committed to that motion, it's pretty hard to back out of it. So what we ended up with was splitting the motion up into a lot smaller segments and the app is basically waiting for confirmation on every adjustment. So the amount that it can move kind of unsupervised would be very small. I think it's less than half a degree or something like that.
Yeah. So that was a call that you guys had to make to optimize for speed. Again, so the engineering triangle, good, fast and cost effective. But for us to do firmware design fast, effectively, was a compromise between the app development team and the firmware team. So the app team had to kind of maybe do a bit more coding on their side to then decrease the amount of work that was going to be happening on the firmware side.
We put the app in front of you and I think you did like this to it. And the first firmware we came out with, it would queue up the commands. So every time you pushed a button, the app would send a new command to the firmware. And the firmware is still busy processing the previous command. So it would queue up the command, which we thought was a great idea, right? Because that means everything you tell it to do gets done. But, eventually you do that and something would run out of memory and the thing would just crash, which looks embarrassing. But even if you didn't manage to crash it, you're now waiting 90 minutes for it to finish processing all those meaningless commands before it can do anything. So we had to rethink how how we did that.
Yeah, I had a discussion with a client today actually about functional testing of piece parts of a project. So, we try as fast as we possibly can to get something that is meaningful. So in this case, it would be some circuit boards that we've created. Even before that, we would get off-the-shelf circuit boards that are available to us, wire them together. We would get some firmware running that was going to be representative of what the end product might be, and we would have a demo app. But the particular case you were talking about was kind of like the first demo device where all the teams come together and they basically try and get this thing working. And usually what happens is the teams that have been working on it, it works for like all the general use cases. But then when...
And we give it to the user and they break it.
Yeah, and that's always the best testing is give it to the end user or someone who's from outside of the engineering team actually trying to use it. Emulating the end user experience as early as possible is one of the best things you can possibly do for a product development. And we do have automated testing and things like that, but the automated tests will, you'll never create a chaos monkey automated test unless you actually really have to.
We might one day, but yeah, we don't have end-to-end tests between the app and firmware yet. So
yeah, those things are hard, but firmware is hard. For some time now, we've partnered with cycling tech company SRAM on their pressure sensor devices, including the recent release of TyreWiz 2. How do we help design the firmware for TyreWiz?
Yeah, so SRAM already has a pretty good embedded team that did most of the design for TyreWiz. The first thing is when we're working on a customer's code base or an existing code base, we try to be conservative and fit within their vision of what the design should be like.
Yeah.
So in this case, they were a bit short and they needed our help. Most of our work was on testing and like the stuff that happens on the factory floor. So interfacing with, I guess it's not really firmware because you're running it on a PC with a lot of USB devices, but interfacing with the end-of-line fixture, we call it, basically, to program and calibrate the sensors. The first TyreWiz was done in a separate build system. And so we helped with porting that into SRAM's newer build system. I don't know if we can talk too much about that.
The build system is basically to take the code and to be able to...
Yeah, I don't know. It almost needs its own area of engineering, like build engineer or something. But the build system is the software that you use to basically compile other software. So in firmware, the build systems can be pretty intricate and pretty customized as well.
So it basically ends up in flashing that device with the code that you need.
And there's software for supporting the testing and all of that. So actually, I probably would say, like, as firmware engineer, I do spend like 60% of my time writing software that doesn't go in the devices. That's sort of decreasing a little bit, but there's a lot of testing software, and you usually run your tests on a PC. Like with the Bluetooth stuff, I said we don't have apps to do Bluetooth tests, but we have software that you can run on a Linux workstation that can interface with Bluetooth and run a set of predefined tests. So SRAM was a lot of that using their systems, obviously, but they have stuff like that. We did debug some of their issues along the way, but it was a collaborative effort, I'd say. We got plenty of support from them as well.
It was a project where we did a whole new electronics design. A lot of the challenges we met were from COVID. They were hangover from COVID. There were some chips that went end of life, and also some ways to decrease the cost of the device by using new chips or actually eliminating some chips from the system. So
the main change was the pressure sensor, which was the most important, the most expensive component, I think. And we've redesigned that in electronics. It was actually quite a different design. It wasn't as straightforward as just swapping out one thing and everything works the same. The way that the calibration works was fundamentally different. I don't know if I should talk about that too much.
We can talk about that.
In the end, the sensor's slightly less accurate, but it's accurate enough for the user that they're probably not going to notice the difference. But it was a pretty big change in the firmware. So we did do the firmware to implement that sensor module and fit it into the existing code.
But that's a classic case of sort of engineering triangle again. So whatever the user experience really is, choosing chips or firmware code or whatever that satisfies the end user experience. If the user doesn't need 0.1% accuracy and they only need 1% accuracy. Maybe not applied to this particular case, but then
that's pretty close. I don't know.
Then you need to, well, you should, as an engineer, holistically choose components and systems that are going to satisfy that. And in this particular case, having a pressure sensor, which was much cheaper in a way, and then creating supporting electronics that basically still gave us the required accuracy, had a bit more complexity in the firmware code, had major advantages to sort of bill of materials, cost of goods reduction, and being able to get that end device down to a price point that was more acceptable by many users. So I think the number of sold devices was, increased dramatically because the price point was being able to be decreased. A lot of it due to selection of components and then the non-recurring engineering, the NRE up front that's required to do that engineering to get the thing to work.
Also, a lot of time spent both by us and SRAM on just characterizing that new sensor and how it needed to be calibrated.
Yeah, so when we choose any chip that goes in a different product, we have to know it intimately. And Sam's come across this many times. Most chips will have a data sheet. The data sheet could be 10 pages long. It could be 10,000 pages long. Like some of them are, to low thousands of pages long. And when you start using different modules in there, the data sheet is usually right, but there's usually bugs. And those bugs are usually some sort of electronics nuance that crops up.
I mean, when it breaks your code, you usually call it a bug. Sometimes if you read it, it's a bit technical. Maybe it was supposed to work that way all along, but you do have to be careful and read the data sheet when you're interfacing with stuff.
So, when we go through a project for any IoT product, we're choosing chips usually that we've used before, that we know work and we know where those bugs are. Any new chip that we put in, we have to basically understand it intimately, because that chip is then going to be purchased thousands, tens of thousands, hundreds of thousands of times, and the user experience needs to be seamless, right? We need to be able to be designing systems which are going to work in this particular case, minus 40 degrees Celsius.
I mean,
all the way through to say 50 degrees.
The user of TyreWiz won't know the difference between TyreWiz V1 and TyreWiz V2, but in terms of the firmware, they're very different. The stuff SRAM already did and the stuff we added to it. But they both do the same thing, so the user won't know the difference, right? Which means we did our job. But
Firmware was one part of it, and then obviously the testing. We have a PC that basically connects to a fixture using USB. And then we put a partially assembled or fully assembled device into that fixture, and then it will do things like start it up, pressurize it, do a low pressure check, high pressure check, put a calibration in there, then it'll do a third point pressure check. So the calibration that it got put in there, it'll check that the pressure that it's reading or that it's outputting is the same as what it's expecting. It'll do things like functionally test all the other things like the accelerometer or temperature sensors, things like that. And creating the calibration system is inherently a part of kind of firmware design.
Yes, you need to write code that's in your firmware just to talk to your testing software. I think one of the things we're trying to do with Cranio is have the tests use the same API that the production applications are going to use, because that's something I've noticed, that you end up writing this special debug interface code that is intended to never be used by anyone except engineers. But it takes a lot of engineering effort just to maintain that. And, if you wrote a good application interface, then you don't have to have two interfaces, one for engineers and one for the app. Right?
So, fair enough. Yeah, we kind of did the same thing with ShockWiz, right?
So I was much less experienced with ShockWiz. But it works. But yes, it has a special unit testing interface, and there's all of these different features and functions we put in there for testing that the app never uses and never has access to, which there might have been some useful stuff we could have snuck in there. But
As we said before, we're currently working on our very own data logging and control system, Cranio, to make it cheaper and easier for everyone to develop their own digital solutions. One of the key components of Cranio is the library of firmware that can be applied to almost any conceivable application, using our experience developing firmware for different clients over the years. how did this project begin, and what have the challenges been thus far?
I think you've been trying to make something like Cranio since before I even started, but
Well, yeah, firmware's always been a challenge. And before you started, obviously, we were creating different electronic devices. We're pretty good at doing electronics design, but firmware is a real art of its own. And we've tried over the many years to do things in different ways, and we've had varying success. But whenever we try to develop a new product, it seems like there is a large amount of rework or doing things in a different way. And so Cranio is kind of a combination of just the experiences we've had over the years. And Sam and I think we were away in America at SRAM on one of these conversations back in, say, 2018, and we kind of made the decision to say, let's just do it one way so that we can apply the same code or the assets we've created, and we can reuse them in different
I mean, in a way,
projects.
it's similar to what SRAM was doing with TyreWiz. Basically, the way they used to do things is, a firmware engineer would set up a new project for every product, and then each project would be self-contained and use all its own tools. And the engineer would write all the interfaces that didn't exist, and they use the SDK from the microchip vendor. But there's a lot of stuff you have to do. Especially for some of the more complicated sensors where there's not just a library, you have to understand the physics behind those sensors.
Yeah.
So SRAM started unifying all that stuff into one build system where there's shared libraries for all of their products. And you can still build individual products, but they are able to share code from other products rather than all being self-contained. So there are advantages to having things be self-contained and independent, but when, you've got to do a lot of them and you have limited engineers available, it saves people's time if there's only one source of truth, basically.
SRAM's a seriously impressive client of ours, and, they turn out millions of widgets which are IoT, mainly Bluetooth-based, and, having a single source of truth or a single build system which everyone can work on, which means that you can have one engineer.
We hadn't seen that in 2018, though, so we can't. We weren't copying it. But it's a similar thing with Cranio. I think we did have some attempts to do things that way, but it was always a bit rushed. And when there was a new demo, we'd just spin up a new project. A lot of stuff was being replicated or it was copy pasted. And I think the worst example, which again is a bit technical, but there was a library that was written that was supposed to use an SPI interface. And at some point, the external chip had been changed to use, or it was the same chip, but they were using the I2C interface instead. And the programmer had put a big define SPI underscore I2C underscore in their header file. So the code all looked like it was for SPI, but it was actually for I2C.
Yeah, right.
Like the first argument or the address argument was ignored or whatever. I hope I haven't messed everything up there, but there was some issue like that, which, it was a bit frustrating to deal with stuff like that because you read the code and the code leads you down a rabbit hole that isn't how it actually works. And you never want to be working on a code base like that. We were thinking about, working with the existing code base and cleaning it up, but we had, I think it was actually the HydraTune, we had to come up with a proof of concept for that, and we realized that the microcontrollers we had been using weren't powerful enough. And so we took the opportunity, like switching to a new microcontroller, we'd have to redo a lot of work anyway. Why not start it as a new project?
But we were also very specific about what we were trying to do. So, we know that we're interfacing with sensors. We know we're outputting things to actuators. With IoT and with Cranio, we're always talking with some controls device. So it's either via Bluetooth or an app or the internet. So we have very specific requirements on what we were trying to do. And we then looked at different operating systems. So there's, a plethora of different operating systems we can use for IoT. We looked at RTOS, real-time operating system.
Yeah, there weren't as many in 2018, 2017 as there are now, but the main one was free RTOS, which we've kind of been inspired by. But the big thing about Cranio really isn't the low-level scheduling. It's the integration with the high-level API. So we designed the firmware in a way that it's easy to interface with it from a higher-level programming language by using the Google protobuf messages. it's not just as simple as just use protobuf, but we design our structures so that it is easy for something outside the firmware to control it.
Yep.
And then the firmware's focus is on making that interface as flexible as possible, but not necessarily defining exactly what the user's going to do with it.
Yep.
So even in HydraTune, the app has a lot of flexibility in how it can control the hardware. So for things like we were talking about how the app can't move it too far, but that's a restriction that we can configure when we build the firmware. So the app does choose how often it wants to send messages and all of that stuff.
Yeah, so that design's given us the ability to have a single device that can operate by itself, a microcontroller that can talk to another microcontroller, a microcontroller that can talk to the internet or an app via Bluetooth or cellular or Wi-Fi or even LoRa, those sorts of things. And then that same API is all the way through to, say, the internet, the web interface or the app itself.
Yeah, so it's been designed so that it is easy for a web browser to render the different data structures we have. The challenges are that it's very much not a REST-compatible API, which can confuse the web developers. So we try and solve some of that in the back end by like converting parts of it to things that are a bit more familiar, but we can also have React apps that talk more or less directly to firmware. It gets translated through all our stack.
Yeah, and again, that's due to limitations of resources. Having to run a web server on a little microcontroller would mean that microcontroller has to be a bigger device, has to have more complexity, can't be as cheap as we want it to be.
I think something people maybe don't realize, because as humans we're used to reading natural language, but parsing text is one of the most computationally expensive things that a lot of firmware ends up having to do, because it seems easy because you want to create an interface that you can understand. So you'll do something where like you use human readable English command words to control a firmware, but that's a trap because it might seem like it's easy because you can understand it, but it's actually doing things in the hardware that are not easy for the processor to deal with, which is why the performance isn't so great. So a lot of web-based stuff is great, but it's all based around human understandable text and
having a computer that's super powerful.
So as a firmware engineer, if I want to see the human understandable representation of an object, I have to attach a debugger to it, or I have to attach an external tool. I don't just see the human understandable representation. So
the constraints of the microcontrollers that we're working with is a major part of the design in which we've created Cranio to try and do IoT lower cost, faster and better. And it's definitely getting to the point now where we can apply it to nearly any application. We've got a couple of big projects like HydraTune and wear detection. We've done a project for WestTrack with a fan controller device, which was, it was up and running within a week because we had the same firmware that we know is tried and tested with certain electronics. We built a specific electronics design to control this fan and have some inputs, applied the Cranio firmware to it, wrote a special small bit of code that did that control system, and it was done within weeks. So that's kind of the thing we're trying to do with Cranio and trying to get more IoT done in faster time and lower cost for customers. But it comes with a load of work in the background that we've had to do, but it's all for the benefit of everyone else. So, which is great. Do you want to talk about anything else with firmware?
C isn't really a script. It gets compiled to assembly.
C code is firmware, and C code is a funny one because C code is the most performant coding language that every other coding language gets compared to.
It's the best performing practical language. Like, we're past the stage of people writing hand coded assembly, but we do need to do that sometimes, but not that often.
Yeah. So one of the challenges with firmware is writing code in C, and C code is highly performant, but also it's kind of seen as old school, and there's not many people who actually do C code, I guess, these days.
Yeah, it's a bit niche. I mean, like you said, there's Rust, which seems extremely popular. The challenge I had with Rust was that it requires the C standard library to even work. So you still need C to get Rust to work. At least when I tried it. Maybe they fixed that now. It's probably a good choice if you're developing a web browser, but there are still places for C programming.
Yeah. So C programming is its own skill set, and C programming on a microcontroller where you're interfacing with the electronics and having to understand how to use registers and allocate memory and things like that, it's an art of its own. So when we're hiring firmware engineers, we really do look for people who have gone down that path, not just use C code in some software project, but actually using C code in an embedded project and working within those things.
Yes, I think sometimes in software it's more of a challenge of finding the right tools to stick together. And of course, being able to write code yourself is still important. But I think in firmware, you do need to be able to write your algorithms yourself sometimes, especially with stuff like ShockWiz, which doesn't, it's unique. It's the only thing that does that. And it has to do it in a very resource constrained environment.
Yes.
And you have to have an understanding of how do you write, data analysis using C algorithms. The first version of ShockWiz didn't have a floating point unit, which is something that you would take for granted in higher level software, is that you can just multiply two numbers together or whatever. But in ShockWiz, because there's the first version of it, because there's no floating point unit, that actually becomes a performance bottleneck because it has to fall back to software libraries to do that mathematics. So instead of using a normal floating point number, you might end up using a fixed point number. It isn't as big a concern, and most processors have floating point units now. It's only the really cheap ones that don't, but that's something I always remember, and it was pretty fun actually having to solve those challenges with ShockWiz. Yeah.
We love meeting people who do interesting things. If you've worked on any embedded design projects, please contact us. And we'd be interested in meeting lots of people because it's a very niche thing to do, and it's also very hard. So finding good people in firmware engineering is always interesting to share stories, war stories. That's all for today. Thanks everyone for listening in. Feel free to like, subscribe and leave a review. Have your say. Hot takes are very welcome. Until next time, make it good, make it fast. See you soon.